Okay, so there are three important principles involved in this first part. The first is work. So work is just force times distance. Since you know how far the car slid, and you know the force that was applied, you know the work that was done. Now, to keep going, you need the net force. So the net force here is just the frictional force, because after the cars collide, the frictional force is acting on the cars to stop them. And you need to know how to derive the frictional force from the normal force. So the frictional force is just the coefficient of friction times the normal force. So using all that, we can derive these equations and solve for friction. So now that you know the forces, you can use Newton's second law to find the acceleration of the car after the collision. So now you're given the acceleration of the car after the collision, and you use kinematics to figure out the velocity of the car immediately after a collision. So right after the car and truck collide, you can find the velocity of both after the collision using this equation here. Now you have the mass and velocity of the car and truck after the equation. Since momentum must be conserved, you can use that to solve for the initial velocity immediately before the collision. Now after you know that initial velocity, you know the acceleration of the car and truck, the maximum acceleration. You also know the final velocity. So now you have another initial velocity, and this velocity is the velocity of the car and truck when they entered the intersection.
The first thing we have to do is find the work that was done by the car and the truck. So work equals force times distance. The force equals friction. The force here is going to be the friction from the tires, and to get mu for the friction, we get frictional force over normal force. So the normal force in this is always mass times gravity. So for the car wheel, we're going to start out by getting the frictional coefficient of the car wheel, which is 100 over 130, which is the frictional force of the normal force. And that's 0.769. For the truck wheel, it's just 70% of mu sub c, which is 0.538. Okay, so the mass of the car and the mass of the truck is this in kilograms. So we know that the force is just the frictional constant times the mass. So that's what we get the force. Work is force times distance. We know the force the car had was this, and then we know that the distance it was 8.2 meters. Same thing for the truck, but it was just 11 meters. The work that was done by the vehicles was the minimum amount of energy that it takes to move them. So we get the energy equals just what the work was, which also equals 1 FMV squared. So we can get the final velocities of the car and the truck, but they're the magnitudes. So they're the vectors of both of the dimensions of the x and y. But to calculate to calculate the collisions, to calculate the momentum in 2D, we have to separate out the dimensions. So to get the momentum of the car, the final in the x direction, we have to get the momentum and multiply it by the cosine of whatever angle it was at, which is 33. And we do the same thing for the y, but it was sine instead of cosine. And then same thing for the truck. So the momentum of, so then we get all the momentums in the separate dimensions. We know that only the truck was going in the x, and only the car is moving in the y. So all of the x momentum is the momentum of the truck, and all the y momentum is the momentum of the car, right? So then momentum is over mass is just velocity, so we can get the initial velocities of the car and the truck like this, and there they are.
So using this, we find that the initial velocity of the truck when it entered the intersection was 12.5 meters per second, which is faster than the stated velocity of 6.7. The maximum velocity of the car, given 3 meters per second acceleration for the car, is 8.831 meters per second. But the car had to have been going 12.81 meters per second according to our calculations over here. So the car and truck were both lying.